Welcome back to Engineering Simplified. In the last video, we talked about the inverse kinematics of a robotic wrist. And in this video, let us do a numerical example to really drill down the concept. So the question is, it asks you to do the inverse kinematics that places the end effector of this robot at the following orientation. So first things first, I see the word orientation and no position, so I know that the question is talking about the robotic wrist. Even though it doesn't mention the robotic wrist anywhere, but since it is only concerned with the orientation and not the position, I know that it just deals with the robotic wrist, which again is the last three intersecting axes of the robot, which are marked here for this robot: theta 4, theta 5, and theta 6. So, first and foremost, what I have been given is a rotation matrix, and I need to find out theta 4, theta 5, and theta 6. Now, what I do is I first mark out the reference frame, my x-axis, my y-axis, and my z-axis, where my y-axis is going into the plane. So here are the steps that I'm going to follow to get the solution. First thing first is I mark out the reference frames, which I have already done. Second is I write out the forward kinematics of the robotic wrist in terms of the variables theta 4, theta 5, and theta 6. Then in the third step, I'm just going to compare my forward kinematics, my answer from second step, with the rotation matrix, which is this one. So I just compared the two things together and I solve for theta 4, theta 5, and theta 6. And I get those values. Isn't that simple? Right? So let me show you how that is done. So I just want you to recall that for a 3D robot, we talked about this a few videos ago, that the x rotation matrix, that is the rotation about the x-axis, is this, and the rotation about the y-axis is this. And if I go up and I see, so if I want to write out the forward kinematics of the robotic wrist, let me write it out here. So I know that there is going to be a rotation about the x-axis by theta 4. So it is going to be an x by theta 4, followed by a rotation about the y-axis by theta 5, and followed by a rotation about the x-axis by theta 6. So this is my forward kinematics of the robotic wrist. Now I know my x rotation matrix is going to be made in this manner and my y rotation matrix is going to be made in this manner. And all I need to do is I need to replace the theta with these theta 4, theta 5, and theta 6 in this and this. So I have done that and I use MATLAB to do all the calculations and I end up with this 3 cross 3 matrix. And so I am done with the first step, I am done with the second step, and now I have to do the third step, which is comparing the forward kinematics to the rotation matrix. So this is me just writing out the rotation matrix again, and now I just need to compare the two. There are many ways to compare the two, and one of the ways that I see a lot of students doing, which is not correct, is they just take one of the terms and compare the term to the other one. Let's say for this case, a lot of you might be tempted to do this. You might be tempted to just take this term and compare it against this and get the solution. However, that is not a recommended method, because you might be missing out on one or more solutions and doing this, and there is always a chance of getting, like, being in the wrong quadrant. Because if you know that there are four quadrants, right, and um, and your cosine can be positive in this quadrant or in this quadrant, right? So it can be either this or this, so it can be either this angle or this angle. Anyways, let me not digress too much. So the better approach is to make use of as many equations as you can. So what I would do is, what I suggest you to do is, I suggest you to take these two equations, this and this, and compare them to this, And what you do is you square both of these equations and you add them up like I have done. So what happens is you square and add them up, so you get a sine square theta 4 and a cosine square theta 4. So when you add them up, sine square plus cosine square becomes 1, and on the right you are left with numerical, and doing a bit of manipulation you get this sine of theta 5 equals to plus minus of this. And I already have this equation cosine of theta 5, so I can compare it against this. So I have this equation 2. So I have equation 1 and equation 2. I divide equation 1 by equation 2 and I take the tan inverse. So I notice that now I get two different solutions, theta 5a and theta 5b. The 5a is the one that I obtained from the positive sign. The 5b is the one that I obtained from the negative sign, and both are equally good solutions, theta 5a and theta 5b. Similarly, what I do is I find out theta 4a and theta 4b again using the other two equations, which is this, and dividing them up. I get theta 4a and theta 4b, and I get theta 6a and theta 6b using these two equations, this and this, and this and this. So notice that I have got two sets of equations and two sets of solutions, theta 4a 5a 6a and theta 4b 5b and 6b. Here are the solutions that I get. So these are the values for the first set of solutions, these are the values for the second set of solutions, and I have even drawn out the robots at these two different solutions. And you see that although the position of the end effector might be different uh, in the two drawings or in the two simulations, and it like I think they probably are different at a different position, but the orientation which is given by these three axes, the xyz of at the tool tip or the end effector is the same. So you see that since we set the forward kinematics of the robotic wrist equal to the rotation matrix and we solved them up, so what we have done is we have ensured that the orientation of the end effector is the same as required, and we haven't taken into account the position as of yet. So in the next video, what I'm going to do is I'm going to talk about how do we do the inverse kinematics with position as well. Because in a real life scenario, you would want the robot to go to a certain position and then approach an object or whatever it needs to manipulate at a certain orientation. So both the position and the orientation is important. So in this video, we have talked about orientation, which was equally important, and in the next video, we are going to talk about the position of the robot as to how to do the inverse kinematics using the position. And then we can combine the position and the orientation together to get the full formulation of inverse kinematics. Hopefully you are finding this video series to be useful, and hopefully you aren't finding these videos to be too tough. If you have any questions, doubts, leave them in the comments below. I will make sure that I get back to you. And if you have any suggestions as to how I can make these videos better, or if you find these to be boring or challenging, just do let me know so I can modify my teaching style accordingly. So thank you for watching, and as always, see you in the next video.